Welcome back. We are in Chapter P, Section 4. This section is all about what is called the binomial distribution. So, it turns out we don't always have to start from scratch when computing probabilities, meaning we don't need to write out our full sample space and then count things and turn it into a PMF table. If our random variable has a well-defined distribution, we already know the PMF. In fact, it's a formula. So there are many well-defined distributions, both discrete and continuous. This chapter focuses on a single discrete distribution called the binomial distribution. There are a few requirements before you can use this, and you have to say yes to all of these. So your random variable x must be counting the number of successes. The number of trials, which we'll call n, is fixed. Each trial can only have two possible outcomes, which we label success or failure. The probability of success, which is p, is constant from trial to trial, and all of the trials are independent of one another. So, for example, flipping a coin 3 times and counting the number of heads. So continuing on with our example we've been using. Well, our random variable x is the number of heads. We're counting heads, so that kind of means we've defined it as a success. This is good. We have a fixed number of flips, so we're flipping it 3 times. So n equals 3. Each flip has only 2 outcomes, heads or tails. Heads is a success, tails is a failure. The probability of success, 1/2, is constant from flip to flip. So I don't mean that the probability of observing no heads, 1 heads, 2 heads, and 3 heads is the same. I mean, each time I flip the coin, the probability of observing heads is the same. That's what it means to have a constant probability. And yeah, each time I flip the coin, that's independent of what happened the last time. Coin doesn't care. So, pausing here, we have our 5 requirements. If I ask you, is something a binomial, you need to write out all 5 of these. So you need to check them. And if you say yes, then we can say, yes, x is binomial. So we'll do an example of that. Scenario number 1, 60% of all commercial bus drivers are over 30 years of age. Out of a random sample of 25 drivers, let the random variable x represent the number of drivers who are over 30 years of age. Well, our random variable x was the number of drivers over 30. How do we decide if that's a success or not? Well, that is what we're interested in. So we're interested in number of drivers over 30, and we see that we were given a probability. We have the probability of all drivers that are over 30. That probability matches our variable, so yeah, great. Counting successes. That one, don't overthink that one. Don't overthink the counting successes one. We have a fixed number of trials, so we have a random sample of 25 drivers. That's our fixed number of trials, is our number of drivers. Each trial has 2 outcomes. The driver can be over 30 or not. Probability of success is constant from trial to trial. How did I know that? Well, at the top it said 60% of all commercial bus drivers. If I'm talking 60% of all of them, that means I'm talking about my population. What do we know about population parameters? They're constants. So p equal to 0.6 is a constant. And the trials, aka bus drivers, are independent of one another. So if, bus driver A is over 30, that doesn't tell me anything about what the next bus driver B is going to be. Because we said yes to all 5, we were able to say this is binomial. And we have notation for that. So x tilde bin n comma p. So in this case, n was 25, p was 0.6. So this is an example if I ask you what is x binomial or verify x is binomial, go through the process and check your assumptions. And then it's not just enough to say, yep, it's binomial. You need to say which one, because there are infinitely many binomials with different n's and p's. What about scenario number 2? Suppose a clothing salesperson makes sales to 35% of her customers. One day she counted her customers until she made 3 sales. Let X be the number of customers until her third sale. Okay, so number of customers until the third sale. Is this counting successes? Well, we know she makes sales to 35% of her customers, so we're counting customers until the third sale. No, this is not counting successes. This is counting failures. This is counting how many people came in and didn't buy something, and specifically until the third sale. So no, not counting successes, so we can actually go ahead and stop now. Once you say no, you're free to stop. If you say yes, you need to keep checking and make sure you check everything, but we've said no. We already know it's not binomial, so that's it. We just say, nope, this one is not binomial. So now that we know how to verify if something is or isn't binomial, what's the PMF? Well, before we can get there, we need to talk about a piece of it. We need to talk about the binomial coefficient. So the binomial coefficient is the number of arrangements of k successes among n trials. The notation is like that on the left. This is also read n choose k, and it's n factorial divided by k factorial times n minus k factorial. So your next question might be, what's a factorial? Well, n factorial is n times n minus 1 times n minus 2, and so on, all the way to 1. We'll do an example of these. Calculate 4 factorial. Well, that's 4 times 3 times 2 times 1, or 24. So that shows you how the factorial works. Okay, next calculate 7 choose 2. On top we've got 7 factorial. On the bottom we have 2 factorial and 7 minus 2 factorial. So up top 7 times 6 times 5 and so on. On the bottom 2 times 1 and 5 times 4 times 3 and so on. What we see here is there was a 5 through 1, both in the numerator and the denominator. Just go ahead and cancel those out. So this is 42 over 2, or 21. That canceling things out trick is going to be very important here. Also, most calculators have a choose button somewhere on there. Now that we've talked about the pieces, we can talk about the PMF. The binomial PMF for a binomial random variable with n trials and probability of success p tells us that the probability of exactly k successes in n trials is, sorry about the order there, is n choose k times p to the k times 1 minus p to the n minus k. So, thinking about our example, actually a new example this time, switching it up. So, heads and tails, equal probability, not that exciting. We want to see something with unequal probabilities, so we're switching to rolling dice. I'm going to roll 5 dice, and I want to see what's the probability of rolling 3 sixes. So, 5 choose 3, right? 5 rolls interested in finding 3 sixes. What's the probability of a 6? 1 out of 6. So 5 choose 3 times 1/6 to the third times 5/6 to the 5 minus 3, or to the power of 2. So we do that, we can write out what that 5 choose 3 is in factorial notation, and if you do the math, you get 0.0322. So there's a 3% chance of seeing 3 sixes in 5 dice rolls. And if you have a well-defined distribution, you have a shortcut to the mean and variance. So we saw formulas for the mean and variance last time. Those would still work here, but they would be kind of complicated. So we like these shortcuts instead. For the mean, it's n times p. The variance is n times p times 1 minus p, and the standard deviation is the square root of the variance. So, example, let's roll 5 dice, and let's say having a 3 is a success. Well, n times p, 5 times 1/6. That's for the mean. The variance, n times p times 1 minus p, 5 times 1/6 times 5/6, 4.167. and standard deviation, take the square root of that variance, you get 2.041. Now, it is worth pointing out here, again, the mean / expected value, we don't round. Can you roll a dice and get a 0.83? No. But we still leave it that way and don't round. But that shows that just saved us a lot of time, right? So when we can use these shortcut formulas, that is awesome. But you can only use these shortcuts right here on this slide for a binomial distribution. These will not work with other distributions, which would be obvious because you wouldn't have an n and a p. So that brings us to the end of section P.4.